August 17th, 2016. This video is specific to lens flares and what they really are, and the fake sun that we see on the ISS feed, and potentially how lens flares fit in with Planet X research. That's what this video is today. Now, I had a real physicist come forward and share some thoughts with me. I am not going to reveal anything about this person other than you are awesome. Thank you, Boo. You couldn't have come at a better time. I feel that I am onto something. I have a gift, and I don't know how to properly explain what I'm seeing and the patterns that are happening. So for folks to kind of help me fill in the blanks, so to speak, is really cool. So the individual watched this video, and here's what they said. I watched your video this morning of the sun from the ISS. Forgive me if I get a little bit emotional. I don't know how anybody can think that this is the real sun, because it clearly cannot be real. The unending lines of light look like laser beams. The hexagonal lens flares look like hexagonal filters and lenses that have been placed in front of this thing. The large circle is probably a containment for the laser beams. I don't think they've been very successful in containing them, though, as we see lots of beams shining out in all directions. I would say that this is actually a very bad copy of the sun. Wow! I have been saying that for months. That's not the sun. It's a device. Oh, yeah! What does that mean? Well, we'll talk about it at the end of the video, okay? We'll just share the facts first. Then we'll go ahead and maybe dabble a little bit into what that might mean for us here, humans. You know, just not really much, just a little baby thing, right? I have attached a document I prepared that shows you where lens flares come from and how their shape is the same as the object the light forming them originally came from. And that is a very important statement. So let's go ahead and read that little PDF together. Shall we? Yeah! Real inconvenient information, isn't this, Boo? Lens flares. Lens flares occur due to reflection of light inside the lens of a camera. Figure 1 illustrates where an image is formed for an object that is very far away. This would, for example, be an object in orbit, the moon, or the sun. For an object at infinity, the rays of light coming off this object are parallel to each other. The rays are refracted by the lens and converge at a point on the side of the lens opposite to where the light comes from. Excuse me. Real light rays converge at this point, and therefore a real image I forms at this point. See? Real image. Ta-da! This image is what a camera will detect once it adjusts its focal point. Okay. Figure 1. Light rays coming from infinity converge to form a real image I. Not all the light gets through the lens, though. Most of the light is transmitted at each of the two refractions, but a small percentage of the incident light is reflected at each interface. We are interested in the reflected at the second interface because this light is what leads to lens flares. The brighter the object we are attempting to capture an image of, the brighter will the reflected rays be. and the more likely we are to get a lens flare. Figure 2 shows 2 of these reflected rays, blue and green rays. The reflected rays go through 2 reflections and 1 refraction before exiting the lens. Once they exit, we can see that the reflected rays diverge. So the only image they can form is a virtual image. This is the image that forms at the point where the light from the 2 rays seem to be coming from. We can find this point by extending the rays backwards, dashed blue and green lines. A virtual image is not detected by a camera. Figure 2, light reflection at the second lens air interface gives rise to a virtual image. Real image, virtual image. Reflected rays diverge, only one real image. Reflection, 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 reflection. Principal axis of lens. Okay. The incident light rays in figures 1 and 2 were parallel to the principal axis of the lens, shown in figure 2. I sure hope my video hasn't been in the way of some of the words, has it? Oh, I was like right on the edge. Sorry, guys. The incident light rays in figure 1 and 2 were parallel to the principal axis of the lens, shown in figure 2. Something interesting happens when we tilt the lens so that the light is not incident parallel to the principal axis of the lens. Figure 3 shows that if we tilt the lens and view a large, bright object, illustrated by the orange circle on the left, the reflected rays are still divergent. Thus, the image formed by the reflected rays is still virtual and not detected. Reflected rays diverge, only one real image. Reflection, 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 reflection. Okay, figure 3, reflected light rays still form a virtual image when the object is large, requiring incident rays from the edge of the object to be far apart. However, when the bright object is either small in size or seemingly smaller, because it is very far away, something amazing happens. The reflected rays converge and a real image forms above or below the main image formed by the transmitted light. As long as the lower incident ray hits the lens at that point, or above that point, where the ray is along the normal little red line or where it is perpendicular to the surface of the lens, a real image is formed by light reflected inside the lens. This is shown in figures 4 and 5. In figure 4, the lower incident ray is incident along the normal or exactly at the point where the incident ray is perpendicular to the lens surface. In figure 5, the lower incident ray is above the point where it would be perpendicular to the lens surface. Again, a secondary real image or lens flare is formed, this time below the main real image. Reflected rays form a real image, lens flare, above the main image, formed by the transmitted part of the incident light. Interesting. Reflected rays converge to real images, lens flare. Gotcha. And there's the real image. And this one, it's like opposite. Can I, let's see. I just wanted to see both of these for a second. Like up close. Reflected light rays form a real image, lens flare, below the main image formed by the transmitted part of the incident light. Now, since the lens flare is a real image, it will look like the object being viewed. It may be smaller or larger than the main image of the object, but its shape will be exactly the same. The only difference between the lens flare and the main image, besides perhaps size, will be that it will not be as bright. This is because the main part of the light is transmitted and a lesser part is reflected, so the main image produced by the transmitted light will be brighter than the lens flare. So to me, this means, like, if we see like one flare, that's probably the sun. But if we see multiple flares, that's where we need to be concerned. I'm just theorizing, right? I take this goofy thing in space, whatever it is, to be a device. Now, my thought is I think we're actually seeing it from Earth. It might be that object that we keep seeing that we think is the sun or the moon, but it's not. It's like a smooth, white, blue planetary object. I don't know, right? Maybe that's something different. Possibly. What is this thing, and why is it there, and why aren't we being told? We demand to know what it is. Thank you, anonymous physicist of superpower, to come forward. You are awesome. Thank you. Chris Potter, lens flares, research. Lens flare, wonder. Lens flare, fun. Right? Yeah! I'm losing it, and I hope you are too. Have a great day now. Bye. Yeah.